Still, I would like to comply with the time, but I am here to. I also put a couple of slides at the end because today I will address some acoustic techniques we are developing. So mainly I will present hardware development. We are in the process of understanding analytically. So that part, I won't address it too much. I just want to mention what are the new things we are doing, what are the development. But I put a couple of slides at the bottom because before I use near-field optical microscopy to measure the lifetime in semiconductors. So completely different, but just to show you, hey, I'm doing that as well. And the other one is we also wrote nanostructures with SPM using responsive materials, responsive polymers. So yeah. I used to include them during my talk, but then I end up rushing. So this time I took those applications out at the end if we have time, and let's focus just on the acoustic today. Yeah.
Okay. Andres,
yes.
Can I record your presentation and let them in your YouTube channels?
Absolutely. Yeah. Oh, yes. Yes. Yeah. Absolutely. Yes.
Okay. We can start in 5 minutes. We can start. Okay. Just let
it would
the
be fine.
Come in.
Sure. Sure. Yeah.
And we usually to put the presentation on YouTube, and after we have at least 200 views in YouTube after.
I will say, yeah, I will put a link.
It's a nice number for 50. Okay.
Yeah. It's amazing. It's amazing. Go ahead.
You remember at Lima when we was in the university?
Yes.
Some students from there usually to watch in your seminar also in the website.
Oh, I see. Good. Yeah.
Oh, Harold.
Hey, Harold.
I will start the presentation of the seminars, and after I can pass to you introduce your invited talk. Okay.
Okay.
Teldo, will there be more than one presentation today? How much time do I have?
50 minutes is a good time, isn't it? What do you think?
Perfect. It's perfect. It's perfect. It's just okay. That you will not be impolite to me if I have my cell phone here, but every 15 minutes you don't mind saying Andres 15, Andres 30. Do you mind doing that?
And 5 minutes until the end, I can tell you. Okay, 5 minutes before.
Yeah. No. As I said, yeah, that's fine. I will check here.
You mean 10 minutes before?
No, like every 15 minutes, say Andre 15, Andre 30, Andre 45.
Oh.
No, don't worry. I have my cell phone. I have my cell phone here.
That's okay.
What is the size of the university? How many students in the full university?
In full university? Wow.
It's about 25,000 people. Approximately, yeah.
Oh, similarly here. Similarly here, undergraduates and graduates, we're about the same thing, Portland State University. We are at the northeast, close to Washington, close to Canada. Harold, Arbieto, did he work the same place?
No,
or
no.
far away?
Arbieto was working at WGAS University.
How far is from? How far is from?
Unfortunately, he passed away due to virus disease.
Yeah. How far away is from?
Last week, I think by plane is 2 hours. You have to go from here to Brasilia, half an hour and a half by plane, and then take a bus and go to the city.
But first you go by plane. Oh, okay.
Yes, because the distance is huge from here.
Start now.
Okay.
I put to record.
Ok.
Ok. Boa tarde, sejam todos bem-vindos ao seminário online do Programa de Pós-Graduação em Física. Desta sexta-feira nós teremos como professor palestrante o professor Andres La Rosa, da Universidade de Portland. Eu vou passar a palavra para o professor Harold, que vai fazer a apresentação do nosso convidado. O seminário de hoje será em inglês e a apresentação do professor Harold também, do nosso palestrante, será em inglês. Andres, thank you for your visit. Professor Harold will introduce you now. Thank you so much.
Okay. Thank you, Teldo.
Thank you, Teldo. So it's a pleasure to have with us Professor Andres La Rosa. He's a Peruvian physicist. Actually, in the present, is working at Portland State University. So he's a friend of ours, and he started his career at the same faculty and same university than me. And he started also some line of research, the nonlinear physics there in Lima.
Correct.
Yes. So this time he will present a talk entitled Near-field Acoustic Characterization of Confined Mesoscopic Fluids. So please, also you can tell us about some lines of research of your group, just to convey us some kind of, to motivate some kind of collaboration with the local institution from Cuiabá. Okay.
That would be great.
Yeah, I'm not very familiar with your investigations, with your research, so I will let you convey us, okay? Please, Andres, please, go ahead.
Okay, thank you, Harold. Thank you, Teldo. Very happy, feel very happy today. Thank you for the invitation. And as I said briefly before the talk, talking to Teldo, I will mainly focus on the things that I'm doing right now, mainly instrumentation development. However, at the end, I put a couple of slides in case to share with you also that I did some characterization of optical properties in semiconductors, Curie lifetime, and also writing some features on responsive polymers. But I took them aside. I typically include them into my talk, but then I end up rushing, so I prefer to avoid that one. So today we will focus on what progress we have made on the study of this guy, this fluid. So this is the fluid which is confined. Let's assume this is the order of maybe 100 nanometer. It depends how small we make the probe. And typically this is a flat surface at the macro scale, and there are fluids confined right there. Just the confinement makes this fluid to behave very differently. So they are very astonishing, surprising properties that is not well understood. So basically, the properties of this fluid is not well understood. And what we bring is a new acoustic technique to characterize those fluids. How effective these new acoustic techniques will be has to be seen. And that's what I'm here. That's what we are developing. Okay. Therefore, let's go to, let's see my, here. So this is what I was trying to say. This is what we do, the mesoscopic fluid. As you may see, confined fluids might be between two surfaces that are under shear, and therefore they will have an effective role on friction phenomena. But also on other interaction, like in biology, when an object is inside a fluid, they experience a force which is much stronger than is expected. And people blame that interaction to the hydrophobic interaction. So this is a big deal also in biology. And we think we could have some inputs to understand that interaction. How do we do it? The way we do it is what we are going to talk today. So this is what we are trying to address. And this is our technique today. So this is what we are going to do. Shear-force acoustic microscopy. So it's I would call it, there are more than one technique. This is the most striking for our group, but there are actually a couple of acoustic techniques that I would like to share with you. Next, what we have is, let's go quick. This is a list of striking properties of the fluid. Like what? Well, when water is in bulk, you have a value of viscosity. But when you use the method available to characterize this mesoscopic fluid, it turns out that the viscosity increases by orders of magnitude. So what causes this effective viscosity? What makes the fluid to be so viscous? So this is an unknown field. Also, the relaxation time. What do we mean? In water, when you want, for example, when you want to stress, when you want to, a spring can hold and stretching. Sorry for my dog. I closed the door of my room, but I cannot control my dog outside. Sorry about that. However, liquids cannot hold and stress, right? Therefore, the higher the relaxation time of a system, the more solid should behave. So it turns out that these fluids, these confined fluids, tends to hold and stress. So it appears then that this mesoscopic fluid actually is not fluid, it's kind of viscoelastic. So it has viscosity and also elastic properties. On the background of all these unknown properties, then we hear on the literature, we find that people actually claim that fluid might be ice. So you will have some ice at room temperature, and so on. So this is more or less a list of properties that draw the attention or motivate to go into the research of the properties of mesoscopic fluids. These are just a few of them. And in fact, therefore, I said kind of to the motivation. So we're in the section to see what kind of objects we are studying, the mesoscopic fluid. So it turns out that indeed, some groups claim that the fluid near a surface actually is a glue. So this group defends the point of view that the fluid is actually kind of very solid. As you could see, you have a probe moving to the right, so the fluid prevents this guy moving to the right, right? And therefore, they claim that actually this fluid is a glue. This is a glue. However, there is a controversy, and that adds it adds complexity to the problem, because what some groups are claiming that this mesoscopic fluid, this confined mesoscopic fluid, is very viscous. Actually, some groups have papers on Nature that say that they have a surface. They have a surface like this against a substrate, and they are able to measure how fast the fluid goes away from the compartment. And they said viscosity is the same as in the book, even though we are using separation distance of the nanometer. Wow. So it's a controversy here. That's what I'm saying. It's kind for me from claiming, maybe if I bring a new technique, we will shed more light on this, okay? Therefore, I leave with this controversy. This controversy is good for me because they could claim our techniques could have a say on these techniques. Needless to say, I typically post this slide to show that in the proteins, the folding and unfolding proteins is a big area in biology. How the protein quickly orders the way it should be, it is unknown. It is assumed that these patches of hydrophilic and hydrophobic sections are the ones who are driven the fast folding and folding of the proteins. So that's what I said. Therefore, our studies may have influence on these studies of protein unfolding of proteins. Okay, let's see. Let's one. Why don't we? Oh, additional. There are also techniques. You know, we are not the first one studying this. It turns out people have a surface. They manage to have surface of the order of what about 1 micron or 2 microns size, and they are able to put them very parallel to each other. So that is not an issue. That is, they could put it atomically parallel. But it turns out that therefore they monitor the behavior of these fluids in between, and they found that it's critical the separation distance. If you have the right separation distance, you will have an ordering of the molecules inside. And when you do that one, their elastic property increases. When you change the distance, and therefore this is not a multiple discrete number of the size of the molecules, and therefore the molecules have room to move around. So if they have room to move around, therefore viscosity increases. And therefore, the shortcoming from this from these studies, well, the point is therefore, it might be that therefore the striking property of the fluid is that while they're in the bulk and the fluid is in the bulk right there, they have a lot of room to move, and that's what they display the properties that they have. But when you confine them to a room in which you have a few monolayer thick, therefore the molecules don't have room to move around, therefore they adopt solid-like properties and they may become an ice. So those are the trends of a study these days. Therefore ordering might be the answer. The only shortcoming on this one is that now we are talking about distances of a few monolayers of water, for example. But the size of their probe is of the order of 1 micron or 2 microns. So you could imagine that therefore, when you are having two surfaces very flat each other, and if you do that at an ambient condition, it is not unlikely that maybe a dust will show up some there, and therefore it will spoil your results. So this calls therefore for a study in which we need to reduce this area from 1 micron to maybe a nanometer, right? That's what we are. So you will see soon in our technique, what we are going to do is to keep one surface flat and the other one make it as small as possible. Therefore, we will be addressing this area, and therefore the likelihood of the dust particle gets there will be less. Okay, so this is what, therefore, so this slide sheds light that maybe ordering might be the issue to explain the results. So let's see what happened. So right there, okay, so this is, as I said, this is the Shear-force apparatus. They are offering the top of the line claims on this area. And there you go. This is the force apparatus. As again, this is of the order of 1 micron, 2 microns. But it is amazing that with the optical technique, they are able to preserve parallelism at atomic level. It is amazing. Okay, so we are, these are kind of the top of the line techniques around. So mesoscopic fluids have exotic properties, yes. There are good techniques addressing these problems, yes, but there are some shortcomings. First of all, the claims are contradictory. Groups contradict each other. Which one is right? And the second of all, that having lateral size probes quite big, therefore they are they are affected by the presence of unwanted impurities in the ambient. So what to do? There you go. Here is, so this is what I want to share with you. And let me check my time. You see is 1:22. Okay. So we want to study mesoscopic fluids, confined mesoscopic fluids. And again, later on, I may like to share with you some results that we have in different areas. But now let me focus today on acoustic techniques. So let me show you acoustic techniques. We have developed 2 of them. What are they about? First of all, background. You might be familiar with atomic scanning tunnel microscopy, atomic force microscopy. Basically, they are scanning probe microscopies, microscopies, is in which the idea is to have a very sharp probe. In this case, it's a sharp probe, and we have to be able to, at the nanometer scale, be able to scan this sample, to scan it laterally, but keeping this distance constant from the sample, something like this. So that is done electronically. That is not the issue here. So, but that is explained, therefore, what is the basis of the SPM. So what is the issue to keep that, that distance, this separation distance constant? There are different mechanisms. One of them is, you know, that was the how a scanning probe microscopy was born, scanning tunnel microscopy, in which, what is your probe? Your probe is a guy who measures current. So if you keep this current constant, it means that while you are scanning, it might be that your probe is at the same distance from the surface. So while keeping right here, making sure that this current is constant, I mean, your sample will be going up and down, up and down, up and down to keep the current constant. Therefore, this feedback up and down will give you your topography. So that is scanning tunnel microscopy. Shortcomings, your sample has to be a conductive. You have an insulator, you cannot apply it. So soon after, it came atomic force microscopy. Now your sample could be conductive, could be insulator, doesn't matter. Why? Because now your probe is not a current probe, it's not an electrical current probe, it is a force probe. What it measures the deflection of this cantilever. When this cantilever is being scanned laterally, therefore, due to the interaction with the surface, the cantilever will be going up and down, up and down, up and down, so that your detector will say up and down, up and down, up and down. And with these up and downs on your signal, you create the topography. So this will be a replica or your surface right there. So this is the atomic force microscope. The shortcoming is this: the interaction between this guy, the interaction between this probe and the surface is so strong at the nanometer scale that when you have your cantilever approaching your surface, when you cantilever, at some point it just bends in no controlled way, because the adhesion forces overcomes the spring constant from your cantilever. So that put problem for the metrology. So there is a shortcoming here, although it's widely used, but when you want to do metrology to study especially surface interactions, we have a problem. So we are talking about 1990s. At the end of 1990s, one guy came with a probe in which, if we want to measure the interaction between the sample and my probe, therefore, let's put a probe in which the AFM, and we said the AFM just bends because the interaction with the surface. Why don't we put therefore a very strong spring constant along the Z? What is that? It is this quartz tuning fork. Is the one that we use in the watches, and therefore on the vertical, since we are going to glue this guy to the frame of our microscope, the interaction between the sample, between the probe and a sample, and we put a sample right here, it will be very strong. It will be very strong. So so this is the sensor. Therefore, we are talking about at the beginning of 2000, people start using this probe. Then let's say here, and that's the idea. So that tuning fork, remember the tuning fork, what we do is we attach a sharp probe. There are methods to make this probe very sharp, and therefore we shake it laterally, and we expect that therefore, because of the interaction between the probe and the sample, because of this interaction, therefore, that will affect the lateral motion of the probe. So in this case, therefore, we monitor the amplitude right here on this axis. This is the amplitude. And then we approach the sample. So when the tip approaches when the probe approaches the sample, then we observe that indeed the amplitude, you see right here, the amplitude decreases as you are approaching the surface. Great. So once you have that signal, therefore, if you know the amplitude of the sample, then you know how far away are you from the surface. So this is one way, therefore, to use in SPM. Okay, so we incorporate these sensors in our new microscopes. We used to build them. It's not a big deal to build those microscopes. And therefore, there you go. So we claim that this tuning fork sensor, is very stiff along the vertical one. So this is not susceptible like in the AFM. So this is not susceptible to the AFM to be bending by the vertical forces. That will not happen. That will not happen. It's very strong. It will be very strong on this along this digression. And therefore, and now it comes the idea that I want to share with you. So by 2000, by the end of 2000, the idea was that therefore this amplitude decreases when the probe approaches the surface. It might be because there might be some fluid layer that therefore it will be dampening the motion of the probe. So that was the idea. Let me tell you from the beginning, but therefore it turns out that to be wrong. Let me see what I have in the next one. Yeah, that has to be wrong. Why it cannot be viscous? It is because if it were viscous forces, interaction between the probe and the fluid. If that were the case, its resonance frequency should shift to the left. However, and this is when I was a graduate student, as a curiosity, the next is not my data, but was published later on, in which they measure, do you see this probe approaching the sample vertically, and therefore at each sample distance, at each distance, you run a spectral response. Therefore, you measure its resonant frequencies at different vertical positions, far away from the sample, closer, and they did it at a vacuum conditions. So in other words, just to make sure to minimize whatever is present in between, in the orange one, just to minimize the orange region. So this is more or less 10 to the minus 6 torr. But even if that's the case, the resonant frequency shifts to the right. And also you measure this not necessarily at vacuum conditions. And ambient conditions, you observe that one. As I said, when I was a graduate student, that was puzzling to me that that's not true what people claim that they claim right here on the top, they claim that this behavior, they call it shear force. Why? But mainly it's because of the damping. However, as I said, these results demonstrate that it's no dampening. It's no dampening. So what could it be? Therefore, now I go to PSU, and now I had the freedom to do whatever I want. So one of the curiosity was, what is behind this? How can I understand this one? It's not dampening. So if it's moving to the right, the resonant frequency moving to the right, must be some elastic response. And therefore, why not to, okay. Chronologically, therefore, let me test chronologically. What we did was something, let me see here. This is what we did. I will come back to the other technique. So try to understand why the resonant frequency of the probe moves to the right rather than to the left. So we said, if that were the case, why don't we, maybe the probe, since we are shaking sideways and they are never perfectly vertical. So what might be going on is that when we bring the tip close to the sample, what might be going on is that due to this vibration, when the tip is something right here, the tip will be doing tick-tack, right? Tick-tack, tick-tack, because this is tapping on the surface. So that's what we said. If that is true, why do we put a microphone right there, which is what we did right here? So we were aiming to listen the tapping of the probe against the substrate. So what happened? So we monitor, therefore, the amplitude. We know it's going to decrease. We know it's going to decrease when you approach. So we're approaching, and here we are monitoring the amplitude, right? We are monitoring the amplitude. When we are far away, somewhere here, so the probe is oscillating at some amplitude, maybe 4 nanometer, something like that. Then I am approaching, and then boop, the amplitude decreases drastically. And my acoustic signal goes up. So the first reaction was, oh, we are touching the surface. We are touching the surface right there. Therefore, to avoid crashing badly the tip against the surface, let's pull out. Let's pull out. Let's get out. And therefore, I will invite you to reason with me what to expect to these signals to behave when you retract. So what would happen when you start to retract? Well, I would say if it is true that the probe is making contact with the acoustic sensor, I suspect that when I retract, when I go into retraction, the retraction might be something like that, and therefore, right? And the acoustic signal should go something like that, something like this. If it is true, if that's true. So what we did was, the next result is what we actually observe. So this point, we arbitrarily, we call it 0, because we thought that's the surface. We thought it was the surface. When we are right here, there is not a drastic change in the amplitude like that, neither a drastic change of the acoustic like that. As my student told me the other day, said, oh, the tip pick up something going on in between, something is going in between. And therefore, at a given distance from the encounter, you still hear some sound, and your tip is still not free to go. Something is holding this one. And that's why, let's see what we have below, and therefore, this is our hypothesis. What happened is that there is a fluid in between the probe and the substrate. And let's agree with the guy who says that fluid is a glue. So this tip, when it goes going down, touches that glue, and therefore that was the reason the amplitude decreases. So, but then we observed also with the acoustic, and the acoustic was going up like that. But then we said, we keep going, but the acoustic now is going down. So this was our first headache. What's going on right here? So initially we thought, oh, right here we are touching at this point, at this distance, we are touching the surface. And that was the acoustic, the tip doesn't have room to move, and that was the acoustic signal decreases. But it turns out we did control experiment. We use a metal. We use as a sample a metal, and we monitor the current between these two electrodes. And when the current sets up, it's because they are in touch, and that's why you see right here the red curve. And the red trace is telling us that when the acoustic is maximum, we have not touched the surface yet. Oh, okay. So, what's going on? What's going on region C? So what I'm sharing with you is all the progress, all the headaches that we were having and we were trying to solve. At this time, we were just happy to say, hey, notice what we have encountered. We have discovered that this minor fluid with the probe being of the order of, let's see, 100 nanometer curvature, and they emit sound. Do you see? They emit sound, and we are able to measure it. And might be noisy, but look, our signal level is above the noise level very clearly. So we have something here. Therefore, let's see. That's what I'm saying. So, okay, it's curious. So what to do with this one? So before I mentioned to you, Teldo, how much time do I have? 15 minutes? Teldo? Let's see.
Hey, approximately 15 minutes,
okay.
Andres. Yeah.
15, okay. So what we have right here is therefore, and therefore, one thing that I wanted to share with you is that Another technique that we have developed in our lab is the following, that when people discover this tuning fork, this is the one. There is also a shortcoming in how to measure the mechanical response. I will not address that one. So there is a shortcoming. In other words, basically, since this is an electrical system, since a piezoelectric has two electrodes, there's a capacitance, and the capacitance spoil the measurement. In other words, when you take the resonant frequency of the tuning fork, you measure this frequency, but actually that is not the mechanical resonant frequency. The mechanical resonant frequency is something like that. So there is a discrepancy between the electrical resonance and the mechanical resonance. So to prevent that one, we came out with a technique right here. It's in which, right here, we call it Whispering Gallery Sensing, because right there, that slide is very illustrative. Remember, all we want to do is to measure the lateral motion of this probe. That's all we want to do. Forget about scanning probe microscopy and so on for the moment. Just the amplitude, just the amplitude. And it turns out, and this is the theory that we developed at that time in 2005. It might be because this tuning fork is electrically driven. You know, right here we have an electrode, another electrode here. So we drive electrically this motion. And because this is the holder, this is just simply the holder. That is just the holder. And therefore they produce sound. And this sound goes up, it is divided in two branches, and it creates therefore standing waves. And therefore, that's the way we explain it. And therefore, when we place a sensor around the cavity, we should detect some sound. But what is amazing is this guy is oscillating with only 4 nanometer amplitude. How much sound can this guy do? And also spread it out all over the surface.
Andres,
So
10 minutes.
Say it again? 10 minutes. Okay.
10 minutes.
Okay, thank you. So right here, therefore, it turns out that we put a sensor right here. It's like when you go to a doctor and the doctor is placing your sensor around your chest, and they found where do you have more sound. Similarly. So that's what we did. You see, this is our experimental one. And therefore, indeed, we are able to measure very nice the response for the tuning fork. We compare with the electrical one, the red, and indeed, the peaks do not coincide. So our technique is more reliable. So we have this technique in which, therefore, if this is the case, we integrate it into SPM, because now we are monitoring this signal as a function of the distance. And with the sample, when the tip gets closer to the sample, yeah, the oscillation decreases, and therefore the acoustic signal decreases. When you have a monotonic behavior of a signal versus distance, you could implement a scanning probe microscopy. And that's what we did. So we took an image purely from where? Listening. So we'll listen the probe sample interaction from far away. Right here. We do not disturb at all this interaction. We just place it far away, and with that signal, we're able to get the image. So that's what we were having these two new ideas from our lab, and therefore, as I said, this question, like, so what? Well, at least we have a new way to get topographic information. Well, probably what we want to share with you is that we are shedding light onto the dynamics of the fluid. So it turns out very quick, in my 5 minutes, will be that it turns out when the probe is approaching the surface at this distance of 10 or 20 nanometer, this is a metastable state. Metastable meaning is more, the system will be stable if there will be a fluid right there. So it's a metastable. So When you close the surface closer, you put a closer surface, therefore suddenly from the molecules in the environment, a meniscus is formed. And that's why when the meniscus is formed, therefore the coalescence of this vapor water into the meniscus is able to produce the sound. And that's why we hear the sound right here. So that's more or less that we are creating our model that what's going on. Initially, when the probe is approaching the surface, we may create some unstable bridges between the substrate and the probe, and therefore during this region, there is no sound. The amplitude decreases, but it's no sound. It might be because we have at this stage. But at this point, these bridges coalesce, and therefore they form a meniscus. And this meniscus is like the glue, and therefore now you are able to create sound. So these are shedding light that the dynamics of the fluid, what might be going on the fluid formation. The other one is, what is that bump? That bump, where is coming from? And therefore, might it be that when you are pressing the surface on this region, there you pushing the water out? This was one of our hypotheses first. I think that might not be the case. Based on the recent results, what we have found is that we incorporated frequency modulation into our microscope. What we mean is, remember, the resonant frequency of this guy changes when the probe approaches the surface. So what about we use phase lock loop, in which is frequency modulation, in which it allows you to drive this probe at the instantaneous resonance frequency. In other words, the resonance frequency, if it increases, you drive it at resonance frequency. With that approach, therefore, we are able to monitor the change in resonance frequency and with the acoustic one. I'm running out of time. What is my main result today is that this is the frequency shift, the green one, and this is the acoustic signal. But we notice the acoustic signal might be also decreasing because the amplitude of the probe is decreasing. What about if we normalize it? What about if we assume that the probe, the brown one, the amplitude remains constant? So we normalize with the amplitude of the probe. And when we do that one, both coincide. So we are witnessing, we claim, that the acoustic emission from the fluid, it is a channel of energy dissipation on surface interaction. So it's more or less, look like I'm running out of time. Let me see. Let me close with this. Is saying, oops. Okay. This is one of the results. The other one is also we have been able to distinguish hydrophobic from hydrophilic. Do you see? This is a macroscopic measurement of contact angle. So this surface, the blue one is hydrophobic, the green one is hydrophilic, and they have different acoustic signature. So we are claiming that we are providing a technique to measure wetting properties at the nanoscale. Yeah, that's about it. My highlights are the following. Sorry, I didn't provide you the theories behind. We are working on that one. We model the fluid as a spring. It has a spring constant, a damping constant. So that's what I call it conclusions. Here is more a highlights. So what are the things that I wanted to share with you? That there is a questioning for which is very robust. Low dissipation energy sensor is a very valuable one. But look like we have come out with a new technique to measure its motion. And it reflects, it resembles its mechanical resonance very faithfully. So these are the virtues of the technique that we are trying to advertise to you. Second of all, that it is surprising that a fluid which is between two surfaces, right? This fluid right here being so tiny with 4 nanometer amplitude oscillations, and this guy, we are able to detect the sound coming from those, coming from this sound, from this fluid. Okay, look like we are the only group doing this so far. And then one thing in which probably people say the application we could do, I think, at least for wetting properties, since all the analysis is done by the probe, and therefore if we could distinguish whether this guy is hydrophobic or hydrophilic, and therefore in principle, if we were to set up a sample which have patches of hydrophobic, hydrophilic, hydrophobic, hydrophilic, I think we should be able to image those ones. We have not done that one. We would like to do that one. And the one that I was excited, remember I put some exclamation marks, is indeed what is going on between two surfaces that are under shear. As we said at the very beginning, this is a very difficult, it's an unknown field. There are no conclusions there. So we have the data in which it reflects, it resembles, it supports that the acoustic emission perfectly matches with elastic energy from the floor, from the probe. So it looks like therefore acoustic emission is, so our technique is placing acoustic emission as a valid, efficient channel for energy loss in surface interaction. Thank you.
Thank you so much, Andres. You're nice talking. Now
Okay.
we have time for question. I talk in Portuguese now, just for your students. Bom, pessoal, a gente abre agora para questionamento. O questionamento pode seguir a seguinte dinâmica. Vocês podem fazendo as perguntas no chat, né? E aí eu vou passando a pergunta à medida que as pessoas forem solicitando. Vocês podem perguntar pelo chat ou pedir a palavra que eu libero o microfone.
Teldo. Hello.
Oi, Harold. Oi, Harold. Você quer fazer uma pergunta?
Andres, just one comment.
Yes.
I'm not an experimental physicist, but I have some inquiry. So, for example, you can consider some special fluids like superfluids or something like Bose-Einstein condensed fluid in your analysis, your study. Please, just a comment about that.
Sure, yeah. Sorry, as I said, the modeling of this, we are quite behind. And one of the reasons, of course, I get along very well with Teldo and you, but one of the reasons is just for me to share the technique that we have been making progress, but what we are lacking is to put the theory behind. So far, the best I have done is to, open a fluid book. And these fluids are made by, don't laugh at me, but it's like a simple spring in which it has an effective spring constant and effective damping constant. We have been able to do that one. And there are papers doing that one, but also restricted to that model. Now, your question is interesting in the sense that what happens if this guy actually is not a fluid, it's a superfluid, right? What will be its ability to produce sound? What kind of spring elastic property will have there one? Here we are. Our technique could shed light on that one.
Ok. Júnior Gonçalves da Silva. Pode abrir o microfone.
Hi, Professor Andrews. Thank you for the presentation.
Hi, Junior.
Junior, PhD student, Professor Anders.
All right.
Yes.
Awesome.
I studied gravity theories, and I'm not a specialist in the fluid dynamics. But my question for you is, what's the bounding of the viscosity with the resonance frequency? What is how to engage these two quantities, the viscosity with a frequency of acoustic?
Yeah. One way to address that question, interesting question, is this. Let me see. Shall I view from beginning right here? Oops. 1 second. Why not getting? Oops. Yeah, let me go to the on this fluid. Basically, what we do is this: we mimic this guy as an spring oscillator. So you have equal the driving force, and then this is when it's free. But when it's interaction, therefore we will have x dot plus gamma plus the gamma fluid, right? Gamma fluid times x dot plus k plus the gamma from the fluid driving force. Therefore, by manipulating this signal, this is a very simple problem. Therefore, we are able to measure this spring and this gamma. Yeah, we could retrieve that one. But then it is model based. So it is based if this fluid is behaving as a linear spring, which is affecting the motion of the probe. So that is the way that therefore we will say that therefore we could compare therefore this viscosity that we measure from experiment with the bulk viscosity, right, from the fluid. I think that was your question. You have this bulk from fluid from your experiment. How do we retrieve the damping constant from the fluid? Is through this model. So free and with interaction.
Ok.
Thank you. The probe interacts with the fluid and modify the viscosity.
Could you say that again? The probe interacts with the fluid?
Yes, and the viscosity is the same change. The viscosity change because the probe interacts with the fluid.
Yes. The interesting thing of this study is that this gamma from the fluid, this K from the fluid, gamma from the fluid, depends on the distance. Depends on the distance d. So that's what is interesting. It's interesting because the more you confine the fluid, the viscosity increases. And even more, there are reports, not with our technique, with using AFM, in which they report the spring constant, something like this. So when you have a few monolayers, 3 monolayers, 2 monolayers exactly, that one, the spring constant, okay, sorry. the spring comes on the fluid. Oh, my pen is not working. Kind of the fluid. Depends on the distance as well. This is the one that I would like when we share our towards seminar to do more theoretical work here. Because we have the data. We have the data. And so far, the best I have been able to do is to mimic this guy as a linear spring. But a more theoretical sounding approach will treat this fluid maybe not just a simple spring, maybe a multiple spring or other approach. Yeah, so that's the part that I would be welcome to collaborate, because we have the data. We have plenty of, and the beauty of this is this. I didn't have time to expand because we have implemented this in frequency modulation. So in other words, we drive this frequency. Since K is changing with distance, we change the frequency as a function of the distance. So the probe is driven all the time at the resonance frequency. That might be useful for the theoretical model.
Okay.
Okay,
We
thank you.
have one more question from Christian. Christian, can you open your mic, please?
Hi, Professor. I have a question.
Hello. Hi, Christian.
Hi, the model are you using is a rheological fluid model, or
Yeah.
is a linear model?
No, we are just in the linear one. Yeah, no, we are just there. You are right from the previous question as well. To have a rheological one, a model will be ideal. You know, more parameters involved. Like for example, the influence of the curvature, right? The influence of the curvature of the meniscus has not been taken into account. I was working with one student from Peru, but he got a scholarship in Brazil, so he's in Brazil now. So, but he was working like for example, just very quick. When I was talking here, at that time that I was in Peru, my suggestion was that maybe, let me see here. Let's see, very quick. It should be here. No, please. No. Anyway, it was like, you know, when we are approaching the probe closer to the surface, the curvature changes. Oh, there you go, here. And therefore, if the curvature changes, and the pressure, the Laplace pressure should change. So maybe the Laplace pressure is responsible for this change in acoustic. Yeah, but again, I am derailing a little bit. The question from Christian was, yes, this system is exotic. Maybe just a linear model may not be the best one to compare. A rheological approach, taking into account viscosity, temperature, curvature, will be the way to go.
Okay. Thank you, Professor.
Thank you. Now, open your mic. Teldo, your mic is closed. There you
Sorry.
go.
Yes, sorry. My
That's
mistake.
fine.
I was
Okay.
telling that last year in Peru, we are talking about a very cheap EFM. You remember?
Yes.
We can use that model of EFM to study what kind of materials. We can study biological materials, inorganic materials. My question is, we can construct a EFM in your program and study materials from our pantanals, for example.
I will be glad to. All I need to do is to copy, send you all the files, and you build it yourself, because we build everything. We use the machine shop. My students build the feedback electronic using FPGA cards. The program is through LabVIEW, and that's why we are trying to build one at La Uni. We got money. We got the money from the university. They gave us $15,000, so we are going to build that one. And in terms of material, let me show you this. That's what I said at the very end. Let me see here. I'm not. Oops. Please don't do that to me. Okay. How can I go? Okay. Just very briefly, the beauty of this microscopies is that then, for example, this application, this is what we have done too. We have a polymer, and the polymer is P4BP, in which if you insert acid, this guy has a nitrogen centers. We are told they are very reactive. Therefore, we put the probe, and we put it into acid, and then we scan at the areas that we want. Like, for example, like this. The protons from the acid get immersed into the polymer. So locally, the nitrogen centers who now have the hydrogen, so they repel each other, so they swell. And therefore, then you have a technique to write fonts on the surface at the nanoscale. So just to make the point that therefore, yeah, having the probe, you could make it isolator, electrical, give you the ideas for to do many things. For example, in this case, materials. Needless to say that I've been working on before, that probe, the same one that we are using for acoustic, the same one, but this time, now we use optical fiber. No problem. The optical fiber will be a probe. And right there, we send visible light to excite electron hole pairs. This one, electron hole pairs, a pulse one, and infrared to monitor. The electron hole pairs are going to impede a free transmission. So the more electron hole pair you create, the less the transmissivity. But the carrier life, the carriers decay with time, which is an important factor. That reveals the cleanliness, the crystallinity of your sample. You don't have defects, and therefore the transmission of the infrared give you an idea of the carrier lifetime, and you could get, you see, different carrier lifetime on your sample. So this is another thing, like that I said, the same microscope. In other words, going to your question, Teldo. So you build the same microscope. Let me see here, right here.
Okay.
Actually, you build the same thing, but you just change the probe. Then you have a different application. Yeah.
Nice. We have a lot of interest in your project.
Okay. Yeah.
It's very nice to have you with us.
Thank you.
Even online form. I hope you stay well with your family. And in a near future, you come to Cuiabá to visit us, and maybe we can do something together.
We'll be glad to. I will be glad to. Yeah.
Ok. Pessoal, eu agradeço a todos pela participação. Né? Semana que vem teremos mais um seminário. Espero que todos fiquem bem e tenham um bom final de semana. Andres, thank you so much. Have a good, nice weekend.
You too.
See you.
Carlo.
Bye. See you, Andres. Stay safe. See you next time.
You
Next
too.
time.
Yes, stay safe. Bye.
Thank you very much. Thank you, everyone.
Thank you.
Let's see.
Andres.
Yes, I'm looking for the button to end. That doesn't show it.
No problem.
Go ahead.
We can talk
Sure,
a
sure.
little bit. when you have time to go.